All right. I guess still good morning for everyone online and everybody here. I'm just going to start a series of lectures on, like I mentioned that yesterday, about some of the concepts that we can just apply to, well, transportation geotechniques, but also to every other, application that we have in geotechnical engineering, actually. So that's the fundamentals for that. And today we're going to be talking and the first lecture tomorrow we're going to be talking about seepage analysis and fluid flow, right? And for that, we promised this morning that we were going to get into the unsaturated conductivity function, right? Unsaturated conductivity function. So start making like this in here. So I just want to bring a little bit of introduction of the whole need. It's just basically for us to realize, and I probably am preaching to the choir right now in here because you all know that this is important, So when we have a saturated soil mechanics, usually it's been a success is because it was easily and widely implemented, okay? And that contribute to our engineering success all the time, okay? Practitioners found it to be easy to implement. And therefore, we just took the theory to be the only theory that was available and easy for us to do. For unsaturated soils, it's been a little bit more difficult. I was talking on the break with your Professor Barat and about implementation, right? I've been trying for 20 years or so with my lectures and my involvement in the payment community to trying to get them into, away from the moisture content and a more fundamental constitutive models that include stress state variables like suction, right? And it's been a difficult thing, right? When people start talking about suction, you start getting, I don't understand the concept, right? Just talk to me about, and fine, we talk to them about volumetric water content or gravimetric water content, but we in our classroom, in our laboratories, we should be doing fundamental modeling based on suction, which is our, fundamental stress state variable, right? Why? Because, we are, there are many geotechnical challenges that are a function of unsaturated soil. Just to name few, the seepage and the flow through air dams is one of them. Volume changes from expansive soils, and actually this is how unsaturated soil mechanics started in engineering, right? We were only paying attention to expansive soils, and all of the conference available were conference for expansive soils. Thus, that was the only way that we talk about unsaturated soils and the moisture flow and the problems with, the volume change due to the moisture flow. Slope stability, we understand that under environmental changes, we do have big problems, right? This is one of the regions that we can just suffer that. Excavation stability issues is an unsaturated soil problem as well. Bearing capacity, if you have shallow foundations, usually you design a shallow foundation, preferably to be above groundwater table. It's an unsaturated condition. All right. Soil cover system and capillary barriers are very beautiful also, way to use unsaturated soil mechanics because the soil barrier just serves as they hold the water until just start getting evaporated before it leaks down. And the performance of roads and railroad structures. Some of you are. How many of you are railroad engineers here? We have few here, 3, 4, 5. Okay. This is, we actually make all this ballast to be on the unsaturated area, right? We never put this one underwater, all right? So it is a pure problem or a pure condition on unsaturated. And all of the concepts that you're gonna see here also apply for railroad conditions. Okay, so the rate of flow is needed to solve most of these problems, the rate of flow. And this one is regulated to the hydraulic conductivity or coefficient of permeability of the soil. Okay, so how many of you are going to argue me that it's not the coefficient of permeability? Well, it is just a way of talking. It's funny because we talk about hydraulic conductivity, which is the right way to do. But when you graduate and you start talking to your boss, you talk about permeability, right? So I'm going to talk about permeability because you're going to be talking about permeability. But I'm talking about not the intrinsic permeability. I'm talking about the hydraulic conductivity of the soil, all right? So that's the main concept on that. It's just a matter of talking to either practitioners or very pure, fundamental researchers. So, and this one is important not only when we have a steady state conditions. I mean, we're going to go a little bit in here on that, and I'll be a little bit on there tomorrow more on that, but also transient flow or unsteady flow conditions through a porous media. So the water storage properties, I'm talking about the K and I call it K and SAT, the hydraulic conductivity function, right? Hydraulic conductivity function is important for both. But also if you have transient flow, not on a steady state, but if you have transient flow, you're going to need also the storage capacity of the storage properties of your soil, right? That is defined by the saltwater characteristic curve, we're going to see later. So what I'm trying for you to learn is just to get interesting facts of the theory behind flow of water, the Darcy's law for unsaturated soils, how we use that, hydraulic conductivity concepts, and the estimation of the hydraulic conductivity. That's for practitioners, pretty much, And last but not least, for mostly on the research side of it, we talk a little bit about direct measurements and how we do that in the laboratory, right? So I'm going to try to do a little bit of everything. So flow, the state of the flow conditions can be a steady state. That means that it's a long-term equilibrium analysis, and also the transient condition, right? And the transient means only time, right? That the changes with time, right? So all of these problems are water flow that are mostly transient flow conditions. Unless you're doing some stability analysis or a long term, that's how we design actually for a slope stability, is an equilibrium analysis, then we go for a steady state conditions. But most of the problems that we do have that are function of climate or environmental conditions are transient flow conditions, okay? So water flow is going to be regulated by the hydraulic conductivity, as I talked to you, and for both a steady state or transient flow, and also for the water storage capacity or the transient flow. So we have historically described water flow through saturated terms in terms of the hydraulic gradient. And I think Professor Barat talked to you lengthily into this is the fundamental variable to figure out the sea pitch analysis. And it's important to us also to understand that hydraulic gradient should be also our fundamental parameter to explain sea pitch analysis. And I'm going to tell you why. Well, I'm going to kind of go through different alternatives, alternatives that we have used probably for instead of hydraulic gradient. Like, for example, okay, I can use volumetric water content, all right? If you say that the saltwater characteristic curve, is related to the suction, you can convert it immediately to, gradient, right? And the volumetric water content. But so that volumetric water content should not be used as a fundamental. Why? Because not always the flow of water will occur from places when you have high water content to places when you have lower content, okay? And this is another lengthy story there about thermal gradients, hydraulic gradients, and every single, potential gradients due to different concentrations. So there is not always the water can flow from a region of lower content to a region of high water content. So this is not a good stuff to do, to change, to get modeling through water movement. This approach doesn't account for hysteretic effects, the stress history variation, or any variation of soil properties, right? Another word that people have tried is the matrix suction, not the hydraulic gradient, but just the matrix suction gradient. Well, flow of water does not exclusively depend, okay, on the matrix suction unless the air pressure gradient is 0, all right? So this is something that is important for you to understand. Matrix suction, and let's see if I can just do this. Okay, this one doesn't, no, okay. So I can go here. So air and water, what happened is air and water is going to be flowing in the individual phases, okay? Not always going to be the two of them together. Not always going to have flow of vapor going in the same direction as the liquid water, okay? So if you can change, for example, different cases in here, we can have a case when we have air pressure, difference in here, which is, the first one is going to be less, more pressure than the second one. Same thing in here, more pressure for water and for this one, and you still have the matrix suction of 25, port air minus port water pressure, right? Port air minus port water pressure. So if you have minus 25 minus 50, you're going to have a suction of 50 of 25. And if you have minus 50 to minus 100, you're going to have a suction of that. In this case, you will have less suction here, high suction here. So if we use this one as a gradient, the water is going to tend to, supposedly, right, to go through to the point when you have higher suction, right? It's going to be trying to soak water from that point to this point. Look at, in this case, the air pressure is graded and the water pressure is graded. In the second case, you got in here graded port air pressure, but you got graded port water pressure in here, but then you still have the same suction value. All right, the same suction value. In this case, you got port water pressure, but the matrix suction gradient is going to be 0. All right? And you know that if you have port air pressure that are different and port water pressure that are different, you're going to have flow on both phases, you see? So this is just a little example, and the other one is the same thing. You're going to have here more than here, the suction, so the water is going to tend to go through that way, and you still have vapor and water going in different directions, all right? So this is not because this is not a good idea as well, right? So that's why the hydraulic head gradient, I just want to show you a couple of examples, is important, and it should be the one that governs the flow of water in unsaturated salts at one. Together with the elevation gradient, of course, we got the hydraulic head gradient. We're going to have also the gravitational gradient, and the velocity is usually much smaller compared to the other two. So we don't use it much on that unless you have evidence that the water is flowing out. So hydraulic head gradients can be applied to each fluid phase. Okay, this is the important part. Okay, so one thing is the flow of water going in this direction and the flow of vapor going in another direction, and it's a fundamental driving potential for flowing unsaturated in the source we're going to have. And I hope I convince you of that. So the driving potential of water you've been looking at in here, the flow of water can be expressed in terms of energy, and you guys are more on the energy side than I even do. So if you have any point, any elevation, you're going to have the energy due to the the elevation head. You're going to have one due to the port water pressure head, and you're going to have one to the velocity head, and the energy is going to be the summation of the three, right? You know these equations since your undergraduate school, right? And I hope you remember that, those undergraduate students in here. Okay, so this is what we have. So we got the driving potential can also be expressed if you just get the the unit weight of the water out of the equation by the potential of the hydraulic head, right? That's what we have. So we got gravitational head, we got the pressure head, and we got the velocity head, which is usually again negligible if you compare to the other two. So the total head can be expressed as the gravitational head plus pressure head. All right. So this is very simple way of estimating that, whether you have positive port water pressure or if you have negative port water pressure, right? If you have positive port water pressures, still it applies. If you get a datum, you're going to have a gravitational head and a positive pressure head. And if you have a negative pore water pressure, also you're going to have that both of them are going to apply. Okay. So how we use Darcy's law for unsaturated soils? Well, it can be expressed by Darcy's law. And you heard this morning about the Richards equation. And it's pretty much, like I said, I don't know who copied who, because I don't remember what Darcy's law was, from that. But actually is the same concept, but I'm going to see the modification that we can do for the Darcy's law, right, to kind of reflect what Richards equation is, pretty much, right? So we have the flow of water. We got the flow of water in here, which is, proportional to the hydraulic head gradient in any direction, and the proportionality parameter is the coefficient of permeability of the hydraulic conductivity with respect to the water phase, right? So this coefficient of proportionality is what we call hydraulic conductivity, of coefficient of permeability. For saturated soils, this value is usually a constant value, okay? That's a constant value. Most of the cases, right? But that's not the case for unsaturated soils. For unsaturated soils, that coefficient, it has to be a variable, and you saw that this morning, of your suction value, right? Should be a function of your suction value. Okay. I have this one in here, but I'm going to have it. So basically what happens in here, because if we want to use Darcy's law, the K value cannot be a constant, okay? You can visualize, for example, what happens when you do have air into the soil. Remember, to have water flowing, you're going to have a continuous flow. Continuous flow. If you start getting into bubbles or discontinuous flow, like for example, bubbles of air is, they will not flow out, right? Or bubbles of water, if we can call them, it's just drops of water, will not flow. So you're going to need a continuous flow, or a continuous flow. But let's say you do have some air. Air cannot conduct water. You cannot get water through air. Okay, you cannot get water through air. So basically they become kind of a non-conductive channels as well for water. And therefore, the air-filled pores that we got in here in an unsaturated soil can be considered similar to the solids that we got in the soil. Just imagine that we have solids in there, and therefore the flow of water are going to go just through the water, right? And basically we can consider Darcy's law. If we said, okay, these air pockets are like my solids, and now what I need to do is to reduce the water content, right? If we just reduce the water content, then we can use Darcy's law for that, right? So the coefficient of permeability with respect to the water phase is a measure of how quickly flow through a medium can occur, okay? And in this case, unsaturated soils. The different type of fluids will have generate different coefficient of permeability, but one thing is important for you to understand. The coefficient of permeability is not only a function of the property of the fluid, okay? It's also a function of the property of the medium that you do have in there, all right? So that's why we don't use the coefficient of the intrinsic permeability, which is, is related to the hydraulic conductivity by the gamma and divided by the viscosity, right? The dynamic viscosity of any fluid that you have in here, okay? So the coefficient of permeability in unsaturated soils is the variable that we will use, not the intrinsic permeability for you to do, okay? It's the one that has, the units of meters per second. Okay. So you also saw this morning from Professor Barat that the coefficient of permeability is a function of, you can say it's a function of two of the three properties. It's a function of the degree of saturation and void ratio, or you can use the void ratio and water content, gravimetric water content, or you can use the water content and degree of saturation, okay? The coefficient of permeability in a saturated soil is a function of the void ratio. And you have that famous equation with the e to the cube, right? That you all know. Okay? Nobody talk about water content, but the coefficient of permeability in an unsaturated soil is based on the void ratio, the degree of saturation, or the water content. Okay? Water flow through the porous space filled with water. I hope I convince you of that. And therefore, the percent of the voids filled with water is an important factor. So, amount of water content. Okay. So, some notes about this. The coefficient of permeability with respect to the water phase, and I always, remark this because there is another coefficient of permeability for the, for the vapor phase, right? There is another one for, for other phases, whatever you do have. You have a contaminant, for example. Okay. So it will decrease very rapidly as the space of the water flow is reduced. So if your void ratio is reduced, this one is going to rapidly decrease. And not only that, the amount of water, because of you saw the little diagram, in the soil also increases the tortuosity of the flow path, and high percentage of the water in the pore space will be kind of bound. And therefore, an arithmetic decrease in the volume of water in the soil generally results in a logarithmic decrease in the coefficient of permeability. So you see orders of magnitude decrease in that one. Okay. This is to compare for different soils. This is to compare for different soils. For example, which of the, if you talk about saturated hydraulic conductivity, which one is higher? The saturated hydraulic conductivity of a clay or of a sand?
Depend upon the
Saturated.
Sand.
Gonna be sand, excuse me. Saturated means suction zero. so you got that. And what happens is, if you compare both suction curves, right, both SWCCs or soil moisture retention curves, you're going to see that the water content, usually the porosity for a clay material, silty material is higher, right? If we talk about water content, you're going to have a little bit higher value there, and you get into the entry value, and then you go down with the desaturation. For the sand, you're going to have probably less water content to start with, right? And then you do have early air entry value, like, we talked this morning also, the air entry value of sands are much less than the silts and the clays. And the desaturation rate occurs rather fast, all right? So if you just go down with an equivalent graph for the coefficient of permeability for unsaturated soils, you're going to see that the saturated permeability for sand is much higher, right? It's going to start in here when it's saturated. For the clay, it's less than that. But what happens with the sand? That thing starts desaturating rather fast, right? It goes down pretty fast. While if you do have the clay, it's going to try to get it when it reaches the air entry value, it's going to start desaturating rather slowly. Okay? So obviously, the only way that we are going to have degrees of saturation, permeability for the sand less than the permeability for the clays, is when we do have higher suction values, okay, or lower degrees of saturation, like you said. Okay, this is important, right, because it's a concept that that's a great answer, right? What is the coefficient of permeability? You say, well, it depends of the suction value that you're going to have, right, whether it's higher or lower, and that's a very neat thing that we need to understand as well. So what is the effect of saturation in the permeability? The change in water in void ratio is potentially small, okay, in soils of low compressibility, sand material, for example, and its effects on the coefficient of permeability will be also less, all right? Changes in the degree of saturation will produce also large changes in the coefficient of permeability, on the other hand. So it's often a singular function of the degree of saturation, right? Now, that doesn't mean that we have clay materials when we have high volume change, that we're going to need to correct that soil water characteristic curve for volume change, right? because that's going to become an important factor, right? You're going to have a change in there. But usually the compressibility, okay, the compressibility change of the saltwater characteristic curve is much smaller than the change due to the degree of the saturation that we got, okay? So that's very important. So, you know, for the first time we do have that now the void ratio, the density is not as important, the change in the density as important as the change in moisture content of the soil. So the pore size distribution curve are usually used to predict the coefficient of permeabilities. And we talked this morning also about pore size distribution, right? When you get into the grain size distribution and you basically go into the saltwater characteristic curve, basically what you're finding is a pore size distribution, right? It's like the negative of a photograph, right? It's a negative of a photograph. You got the grain size distribution, and now you get the negative, which is the pore size distribution, which is your saltwater characteristic curve. And the same way, you can use the same thing to predict the coefficient of permeability. And I didn't bring the same scenario that Professor Barat's showing here for the grain size to the SWCC, but we have the same, you know, summation of pore sizes that we can just go Childs and George method from the saltwater characteristic curve to the hydraulic conductivity. But we're not going to get into that in here. We're going to get into other estimation more on the practical side of the profession. So the pore size distribution has also been used to estimate the rate of decrease with respect to saturation. Okay, so you know are now familiar with the saltwater characteristic curve. Okay, the permeability function, when you start getting into that, is going to need the saltwater characteristic curve, and you're going to need the saturated hydraulic conductivity. Those are things that I'm very sure now you saw the laboratory, you know, hopefully some of you are going to go out, those in the field, and buy a saltwater characteristic curve device, right, and trying to just measure the SWCC or estimate it. And I'm going to show you some estimation methods as well, right? But if we have that one and a permeability value, we will be able to estimate the unsaturated hydraulic conductivity. Okay. So I'm talking about the 1950s and 1960s when Bourdin and Brooks and Corey suggested that the permeability function can be obtained by the saturated coefficient of permeability and the SWCC. All right. So we're not talking this. We're talking about 80 years ago, right? Not that much, but 60 to 80 years ago. So the soil is assumed to be incompressible for this, okay? And again, we can correct the SWCC for that. This is a very nice thing that we're not going to bring here. But what do you need from the saltwater characteristic curve? Well, you're going to need the air entry value. You're going to need the residual degree of saturation, which is in here when the volume, I'm going to show you in a minute, to estimate, the residual degree of saturation can be ready to estimate kind of a range in which the desaturation is going to occur. And the pore size distribution index, that's how Brooks and Corey call it, but it's nothing but some parameter related to the slope of the saltwater characteristic curve. I'm going to show you in a minute. Okay. So residual degree of saturation, you already saw, is the value where the increase in matrix suction, previous slide, do not produce a major decrease in the degree of saturation. The second, the air entry value, is the matrix suction value that must be exceeded before the air start receding into the air port, and the effective degree of saturation for points within the air entry value and the residual value can be estimated by an equation, okay, which is going to be a function of the air entry value divided by any suction value that you have in the curve or in that range from here to here before the residual, to a lambda parameter, And this one again is for suction greater than entry value. That lambda parameter is related to, this one is the, here we go. This is the lambda parameter here, the slope of the saltwater characteristic curve, right? And they propose this equation in which the lambda is related to the delta parameter, and then the delta is putting here in a power equation with the degree of saturation to estimate the permeability on any one of those points. Okay, I mean, this is a way for you to save a lot of time and money, right? To estimate the permeability function. So this one is a prediction. I'm going to talk a little bit more later on that prediction, but this one is one of the ways that the profession has done it. And I'm emphasizing always that there is nothing like laboratory testing, and you know that. There's nothing like laboratory or field testing, if we can do that. But because you want to implement some of these theories in your profession, okay, or in your projects, I think you can start with something on the predicted side, always taking into account that you're going to have a lot of variability associated with the prediction, right? Uncertainty. So you need to count for that uncertainty because you are doing a prediction. So I'm not advocating for prediction, but I'm saying these are useful if you want to implement, okay? Delta and lambda values are also suggested for different everything okay? All right. So delta and alpha values are also suggested for uniform sands, salts and porous rock, natural sand deposits. But again, if you do have a saltwater characteristic curve, whether you predict or whether you measure that in the laboratory, you can estimate your delta and lambda parameters, right? So the closed form solution becomes, if this is the degree of saturation, you change the delta for the value, and it's lambda over delta, delta over, just come back in. The math is good, so you just can go for that. And then the permeability becomes that closed form solution equation, right? So this one is an important way, what?
Just hold for a second.
Yeah.
I think an online participant are not able to see the equations.
They cannot see the equations.
Just fixing it now.
Okay.
That's it.
Is the material will be available, but yeah. And
ask whether they are able to see now. No. Can you just ask? No. Okay, fine. Please go ahead.
okay.
I think they are able to see.
Oh, it's just the video lagging and some internet connection probably problem.
Now they are able to see.
All right,
Please proceed.
let's keep going then. All right, so this is one of the methods, but I brought a couple of more methods in here for estimating or predicting the hydraulic conductivity function. And those are usually empirical or semi-empirical values that you're having here for that. And it's and they're being derived from the matrix suction versus degree of saturation curve, okay, as opposed to the matrix suction versus water content or volumetric water content, the saltwater characteristic curve, right? So all these procedures are essentially obtaining the permeability, make use of the saltwater characteristic curve in the degree of saturation form, volumetric form as well, and basically is the pore size distribution form that is the basis for the prediction of the permeability. So I got three in here that are important. For this one is already the Gardner equation. This is already, that's the Brooks and Corey equation. And again, this is from different source, but it's the same parameters. This one is another one that works, when it has A and N constant. I'm going to go in for that in a minute. And there's another one that has in here an N prime constant. But most of them, even if they are, are pretty much of the same form. and it's been working, I'm talking about 70 years, people working with that. You know that the petroleum engineering has been using that one way ahead of us. Okay, they're using all this with no problem. Gardner equation, this is the second one that you saw on the list, that has an A and N parameter, and it's very interesting. Gardner is, you saw some of the SWCC models, right? You can use Fredland and Singh. Van Genogten is Van Genogten and all the students, Moalem, Bourdin, all of them are great equations. Gardner is another great equation. The nice thing about Gardner, which I don't like it, but is, it was nice at that point, is basically that is a, kind of a function that requires only 2 parameters. And for those that do modeling, right, it's easy that not to get into getting into the infinity or getting into very unstable programs. When you start getting into 3, 4, 5 parameters, that thing can start making a lot of roots and start making a lot of problems when you model, right? So this one is an easy one to model. A is a function of the air entry value. And I said it's not the air entry value, it's a function of the air entry value, right? And the N value is supposed to be related to the slope of the saltwater characteristic curve. Although we have done some analysis with that, and sometimes I can see that the N value doesn't appear to be the one from the saltwater characteristic curve. So in other words, what you do is you just go, see if I have a little bit of spacing here. I guess I don't need this. I can use my finger, but for example, if you do have your saltwater characteristic curve, right, and you got several points measured in the lab by any of the methods that you learned yesterday, right? I'm talking about in here your volumetric water content or degree of saturation and your suction value. Let me call it pore air minus pore water pressure, and you got all these points. And then you do a solver or regression analysis, nonlinear regression analysis. You input your porosity there, or if it's the degree of saturation here is 1, and then you just put a function to that, right? And in order to do that, you're going to need fitting parameters, right? The fitting parameters for Gardner equation are A and N. For Van Genogten and A, N, and M, so 3 parameters. For if you get into the Fredland and C, you're going to find 4 parameters, A, B, C, and H sub R. Okay, so these are nothing but fitting parameters to the data that you obtain in the field or in the laboratory, right? So this is how you obtain these parameters. You measure the data points. Okay, you go to solver. You just put the sum of the square errors to be a minimizing error in there, and then you put any equation you want, right? That the right hand side of the equation minus the left hand side should be 0 or minimize it, and basically you find those parameters, right? It's a little bit probably high for our undergraduate students here, but you eventually will gonna do that, right? So that's how you obtain those parameters, and those parameters are the important ones because they are the ones that you're going to use and need for the prediction of the K and SAT function. This one is the Van Genogten and Moalem model that I'm now talking about the 80s. And again, you got the K SAT value here. You got your suction value here. Okay. And then you have 3 parameters, alpha, N, and M, that you obtain in the same way. Those are constant, make out of your relationship, and then you use them directly from your saltwater characteristic curve to get your K and SAT function, all right? So this one is more continuous. Gardner is pretty bad, Gardner, the problem is Gardner will keep going like that, through zeros and negative values if you keep going. So just be careful with Gardner, right? For a small range of values will be fine, but not for all of it. Van Genogten are great equations. The only problem with Van Genogten's equations are, that if you are modeling, this guy probably can just get a residual value and flatten down. And then if you have low water contents, you get into infinite values, right? And then you start getting into trouble for that, right? Fredland and Singh equation, on the other hand, is something that you just get that one and just get into that here. That creates some problems as well, right? It's not and a lot of more instability because you need 4 parameters. But it fits the equation to the 1,000 megapascal or 1 million kilopascal that we talked this morning as well. And this is good for the modeling effects, right? So I like that one because of that, if you are modeling. If not, Van Genogten equations are very good, right? Unless you do have a residual condition that is, you don't have enough points, and then the residual condition is going to flatten out pretty quickly for you, right? So this is all. You need to try different models to see which one will work best for you. This is another one, Van Genogten et al. Also, and this one is, again, this one will require the volumetric water content at saturation, the residual volumetric water content in here, and it has a parameter, the famous P parameters. We spent a lot of years trying to figure out the P value for this equation, and they have a name value here, which is a constant, which is assumed to be 1 over n, and this one is from the saltwater characteristic curve. This P value is a constant that describes the degree of connectivity. So between the water conducting pores, some authors have talked about that this depending on the contact angle, some about the tortuosity of that. So there are many theories about that, but this is the parameter that if you change, the whole thing is going to change, right? So that's, that's the holy grail of this equation. It's not easy to that. So, but nevertheless, it's another way. But again, we need more, how to associate this one to the material properties. It's not easy. Okay. We also talk about hysteresis. If the saltwater characteristic curve that you're using to estimate the K-ansat function has hysteresis, therefore you will expect the conductivity function to also have hysteresis, right? And the coefficient of, so you're going to have in here, this is your saltwater characteristic curve, the drying going down and the wetting. There you're going to expect, or you're going to be measuring that the permeability here is going to be the drying and the wetting. Also, you're going to have hysteresis, okay? When you have volumetric water contents, I don't know if I have it here due to the direct relationship between the volumetric water content, between the suction and the volumetric water content. Actually, if you plotted volumetric water content and the permeability coefficient displays no hysteresis effect. It's not that there is no hysteresis, it's just there is no plot, there is no difference in that. And you find this one, so you be very careful with that. The two curves actually go one on top of the other one. What we do, okay, so I don't know, we didn't go through that, but what we usually measure in the lab is easy, but you can do either way. You can measure the drying curve, right? It's easy to put a high suction value, saturated sample, and then you start applying potted pressure or just changing your suction until you get into the drying side of the thing. It's an easy thing to do. There are methods also to estimate or predict the hysteresis effect depending on the soil that you got. I think Pham, one of the students from Professor Fredland, had a very nice couple of papers, or he worked 2 or 3 years on that, when he estimated that the hysteresis might be about half log cycle for sands, about I think it was 1/4 of log cycle for sands, half cycle for silts, and about 1 cycle for clays. Okay, and he demonstrated that with obviously a lot of data. A lot of good data demonstrated that. So you can do is measure the drying curve in the lab, right? If you don't have, now if you have time, you can just go for the wetting curve and do the hysteresis right now, right? And but if you don't have that one, you can actually predict the wetting curve, or you can measure the wetting curve and predict the drying curve, whatever you want to do. But I mean, there are ways to figure out the hysteresis of the permeability if you have the hysteresis of the saltwater characteristic curve. And again, I've been very practical in here on that side of that. This is the effect of the anisotropy on the permeability function. Again, if you do have usually any deposited layer system or any deposits of one layer, right? Usually you're going to have what's going to be the permeability. If you're taking the anisotropy, the permeability in the horizontal direction and the permeability in the vertical direction are going to be different, right? It's deposited. Which one is higher? X, right? You know, X 5 to 10 times, 15 times more than the vertical. So that's another thing that for modeling is very interesting, right? And we include anisotropy. Actually, the results are way different to what we do. We've just put, we always assume isotropic conditions, right? You know, big mistake if we're trying to do something in the field. But it's, you know, less time consuming and we just go for that. If we got something like that, the permeability on the horizontal direction is higher and the permeability on the vertical direction. And therefore, you should expect that there is also a difference between the two unsaturated hydraulic conductivity functions. Do you guys have any questions on that? I don't mind stopping in the middle and then I'm going to continue with the measuring one. All right. Yeah? Yes?
Yeah. While explaining easy model, while explaining VZ modem hydraulic conductivity function, you mentioned alpha as something related to diffusivity coefficient. But if I am not wrong, it is something related to air entry section, right? Inverse of air entry section. If I am not
the
wrong.
air entry value?
Yes, ma'am.
Oh, you're talking about the...
Yeah, I don't remember the slide name, but yeah.
You're talking about the lambda value that...
VZ molem. Van Jenissen molem.
The Van
Hydraulic
Jenissen
conductivity
model.
function.
Okay. This guy?
Yeah.
This guy, alpha.
Yes.
Okay, and again, I'm a little bit of critical about that, but yeah, it could be. You know, there are, it depends on if you use the degree of saturation, volumetric water content, gravimetric water content, okay? For one of those functions, you can relate this one with the air entry value directly. And you said it's 1 over air entry value, right? That's
Yes.
what you said. Okay. And this is okay in one of the functions that we get. But when you start changing the scales and normalizing it to different things, this sometimes may not apply. So you be very careful of that. So it is related to, I like to say that, but it doesn't mean that are exactly being able to measure. Okay. So that's what I think it is. And I don't remember which one of the two functions are the one that you can do that, but the other ones are, you know, perhaps not as, you know, that. The thing is, we read this one, we go through the literature, and then we just put the air entry value there, and sometimes it doesn't work. It doesn't work.
I think he's pointing out the hidden diffusion coefficient, constant.
Yeah.
It's written in the text.
Oh, diffusion coefficient.
Yes.
Constant. Okay, I see what it means. Yeah, yeah. So it is related to the air entry value. Mm-hmm.
Yeah, that's
Yeah.
what.
It is related to the air entry value.
Yeah, it's something.
sorry about that.
The units something 1 over kp or 1 hour meter something. Yeah.
Something like that. Yeah, that's true. You're absolutely right. So this one is not. All right, any more questions? Okay, good. All right. So direct measurements, right? Direct measurements in here. So now, there are different methods that we can do. Like, you know, this is now more into the research side of the question, right? There are two methods that to measure the hydraulic conductivity in the lab or in the field. And there are direct measurements. The permeameter is one of them. The field measurements also use kind of permeability tests to do that. It's a little bit more expensive, but can be done also in the field. But the problem obviously is that the measurements of the permeability have to be done at different moisture content values, right? Because we need the whole function on that. So laboratory tests are more economical than the field tests because, you know, field tests are more difficult for you to control where the water is going, and just to being able to collect the water, and that, okay, this one represents this amount of moisture content in the soil is more difficult. Laboratory gets more economic and more easily to control. There are different procedures to measure the permeability. You can do it in terms of the pore water pressure. You can do it in terms of water content. And again, I bring this over also because we use that all the time. Even if we know that the water content is not the fundamental variable that we need to do, but we do that all the time. And what we do now that even if you can go for pore water pressure measurements, because the high suction values, for example, in the field, you're going to need a high suction tensiometer, which are very expensive. If you have low sandy materials, you're going to be able to get tensiometers that are much cheaper on that. But if you cannot measure pore water pressure, then you're going to need to measure water contents, right? And if you measure water contents, then you go to the soil water characteristic curve and you just go back and forth, right? Go back and forth. And then you can do a more fundamental analysis with the suction value. Okay. All the methods use, again, the Darcy's law of validity. The flow rate and the hydraulic gradient are the variables usually measured during the permeameter test, same way that you learn in your undergraduate school for saturated conditions. The steady state is a flow rate, and the flow rate and the hydraulic head are kept constant. For the transient flow condition, the flow rate and the hydraulic head vary with time. Okay. The steady state method is used usually for undisturbed and compacted samples. You can use any of the two. There is always, when you talk about a steady state, you leave a constant head on an unsaturated soil element. And I'm going to show you in a graph, but I like to summarize before I get the graph in there. And then the matrix suction and water content of the soil are maintained constant. And that's the important part of it, okay? And then when the Q in is equal to the Q out, the hydraulic conductivity is calculated for a particular water content that you got in the soil, all right? So it's the same thing, you just need to change the water contents of the soil. The procedure is repeated for different suction or water content values. The procedure starts with usually saturated conditions, and then you start drying the samples until you get less water contents and different points in that. And the water content must be measured after each stage, which is a problem sometimes, right? Because you're going to need probably different samples, right? You're going to have a sample that you're going to be putting in here, right? And then you're going to put it at a particular suction value or water content, okay? Let's say you're going to control the suction, because you do have the time, you have the apparatus. So basically, to do that, you're going to need to put high air entry stones at the top and at the bottom of your sample, all right? I'm very sure you saw them yesterday in the lab, okay? And then you're going to remember that the suction is pore air minus pore water pressure, right? So basically what we do is we control the pore air pressure, and then we measure the pore water pressure, all right? We control. How do you control it? Well, you control with a particular air pressure supplied. When you can measure with a manometer, you can measure what is the head of your, that you are imposing in there. And then you can put some tensiometers in here and measure, in a couple of points, the head that you're going to have in there, and use the average of those two to imply a head for the whole sample that you're going to have in there. So the coefficient of permeability will be basically the average, correspond to the average matrix suction in the soil. And we calculated, if you use the Darcy's law, it's going to be calculated, you solve for K, and it's going to be the flow of the water, the area of the sample, the time it takes, and this is the pore air pressure, that's the pore water pressure, and you use the average value for those 2 points that you put in here, okay? This is the head already, and basically you get pore air minus pore water pressure, and you get the equation for those two. So this is the way that we calculate the steady state condition in the laboratory, right? So there are limitations, obviously, for that method. It's very difficult to start getting flow out when you have very low water contents. I mean, you can try it, but it's absolutely difficult. You know, you need to avoid evaporation rates. You need to know a lot of problems that are related to the laboratory field. So high matrix suctions are difficult to measure. We are limited by the air entry value of the ceramics, so you're going to need different ceramic stone depending on the soil. If you have a sand, probably 100 kilopascal will be fine, or the 1 bar stone. But if you have a clay, you are limited to 15 bars. I think this is the maximum I can get, 15 bar ceramic stone, which is 1500 kilopascals. What if you want drier than that? It's going to be difficult, right? Water flow is very low, so it's going to take a long time. We're going to take 3 PhD students to measure something, and we don't want that, right? We want you to graduate and get out of here and get a job. So basically, and this air diffusion of water, and you know, all of these problems that might happen when that those specimens are put in a laboratory. And also, you're going to have some shrink. It's going to be volume change when you start lowering the water content of your sample, and now you start getting, you know, the sample detached from the air entry stone. You're not going to have, you know, flow, continuous flow, and so forth. So it's kind of difficult. So we got the transient method, and I'm going to bring in here I guess one that at least I've been successful trying to, you know, getting data out of it, and is basically the instantaneous profile method that Richards and Weeks proposed in the 50s, right? And again, here is the summary. It's a transient flow method. The method uses a cylindrical specimen. Basically, you do have column, and you just put that column in the horizontal direction. Why? To avoid the gravitational, you know, gradient. You just want the suction gradient going on in there. The flow can be a wetting or a drying process, like, you know, we were mentioned this morning. You can apply pressure on one side and let it dry, or you can open one side and just, you know, let it dry, or so forth. So it can be depending on the way the water is introduced to the specimen. The variations, you know, you can measure the water content, and basically we're going to be talking about the moisture sensors. We use the same moisture sensors in there, when we can just basically install them in the sample, right? Those are the sensors right there, and basically you can measure the water content in there, and you can measure pore water pressures also independently and figure out your whole soil water characteristic curve. Usually it's difficult to put many sensors in a column, right? Many sensors. So and you want to do a column that you don't want this to be a huge, because you don't want the flow going up and down on the horizontal direction, okay? Because you're going to need to estimate the amount of time that it takes the water to go from this point to the next point. We're going to see that in a minute. And if that thing has a lot of tortuosity, it's going to be tough. So you can measure only the water content and then get the soil water characteristic curve and get the suction, or you can record the pore water pressures and then determine the water content from the soil water characteristic curve. So again, you can go back and forth with that. Usually these are confined in an impervious tube that is set in a horizontal position. Suctions are measured at different locations along the length of the tube. The pore pressure is maintained at a value, usually the atmospheric pressure, and water flow is introduced for one of the ends. So how do you introduce that? And I think I'm running out of time, right? Am I okay? This one is run out of battery. 12:30?
No.
So, okay, so I'm almost running out. So I'm going to just wrap it up in a second. Sorry about that. So the suction measurements are taken as a function of time, and measurements are taken until the water has advanced through the samples. So this one is important, right? The time. Okay. So you got that tubing here, and basically this is what we did. We got this one, and we had actually made a space for just get tubes in there and get water contents out of that, and then pack it again with the same water content is not easy, because then you have to wait until everything equilibrates again, but it was doable. And basically what we did is we put, soil in here that was higher water content, and soil in here that was open on this side. Soil in here that was less water content, right? Or we just put in here everything saturated or just very high water content and just open one end and just let the water to get out by evaporation. And in Arizona it's very easy to get that evaporation going on, so there's not a problem on that, right? If you have in here difficulties to get evaporation because you have a relative humidity, then you're probably going to be able to induce some potted pressure, right? Or some hair dryer stuff or something that you just dry the soil on one end, right? So that's what you get on this one. Right? And basically you install inside all the sensors that you measure the water content with time. And we put this one for about a year or so, year and a half. I got one of the students working on that, and he was able to get not only for, you can see here that we just were putting material at different moisture content, for example, to figure out different ranges, because when you put one water content, then you are subjected to have, to wait a lot of time for this one. But if you start from different water contents, then it's going to be able to have more points on the K and SAT function, right? So this one is the work that one of my students did in Jacqueline to determine this one, and not only for samples that were intact, but we also did some cracked samples, because we wanted to figure out how the water content will behave around the cracked material. We were working on some of these unsaturated soil problems, right? So the air entry value and the residual suctions were estimated from the soil water characteristic curve. This one is a lower value that we have for the permeability function in here, and there are a couple of theories, but basically you just can go low forever, right? There is a point when the vapor start gaining the gain over the liquid, right? And basically Ebrahimi and Birang estimates that the lowest permeability before you start getting into the vapor phase is 10 to the minus 14 meters per second. So if you see everything on the literature that we do have, I limit this one, whatever values are, we limit it to the 10 to the minus 14. But depending if you have some value here. So you do have the K-SAT is easy to calculate for every soil. You know how to do that. We calculate the permeability between the air entry value and the residual condition, and we limit the value to the lowest value, which is 10 to the minus 14. And basically this is how we put, you measure water contents in here at time equals 0, and the suction value, if you have, sensors for that. And after a time, and I'm talking about, you can do that one as many times, actually we put something to record it, right? And basically you measure the water contents at another time, so you do have the time. You have the space between this one, where the water is flowing out, and with this data you just use Darcy's law and you calculate the equation from Darcy's law, and basically what you're going to need in here is the hydraulic gradient between those points. We use average values, like average suction for that, and basically, that's the equation we use. This is the change in the volume of water between the 2 points. You have water content measurements, right? So you can calculate that. We got the cross-sectional area, the change in time, and the hydraulic gradients. And this one is calculated by the amount of water. It's just basically the summation or the integration between those two points, right? Is the difference between the 2 points and the difference in water contents in and out. So this is how you calculate the change in volume of water. And the hydraulic gradient is also determined by this equation, when the hydraulic gradient in here, the head, is the average of the two suction values that you have. Okay. How do you get those suction values? Again, you put sensors in there to measure the suction, or you go directly to the saltwater characteristic curve and obtain the suctions out of that water contents that you have. And that's how we calculate the hydraulic gradient. These are the points we were able to get. This is one sample that we got only for saturated conditions. Then we start playing with different saturation in here, and we were able to do that. Variability will exist not only in the SWCC but also on this, on the K and SAT functions. And but we were able to get very close to the to the function that we wanted. Okay. The disadvantage is time consuming. The proper flow rate is very difficult to get. If the flow rate, if you're applying, some flow, the flow rate, probably recommended values between 0.2 to 5 centimeters cubic per day, but it's difficult to choose that. If it's too high or too low, it's going to be tough. If it's too high, you're not going to be able to measure the changes. If it's too low, it's going to be crazy. And actually, the accuracy of the test is a function of the space that you have between those 2 points, right? If you do have the space too high and the times too high, there's going to be, the water can go anywhere, right? And you can have more inaccurate results. All right, so almost there. I'm sorry, I'm over your time in here, but you guys have any questions on that one? There is another method of estimating the K and SAT function based on also the port side distribution analysis. I'm going to try to get the material for you guys, to get to that one. But, I wanted to bring a little bit more practical oriented equations here. Any questions that you got? All right. It was clear or you didn't understand anything? What was that? All right. Thank you very much. So what is next?
Lunch.
Lunch. Okay. So I was just between you and lunch. Trouble. Oh, any questions from online? I'm sorry. Well, it seems like there are no questions online. Right.
So we'll assemble here, back here at 2:30 before going to the field for a demonstration session. We'll have one session on measuring methods for the suction. If possible, also hydraulic conductivity. If possible, I'll show some methods quickly. So because I see that a lot of questions were there yesterday on tensiometer and other things. Adarsh asked. Yeah. So I'll try to explain today before we go to the field. Yeah, sure. Thank you.